Okay, so the last little while here, okay, we've been doing a lot of stuff to do with work and energy. The other day you got some conservation of energy stuff, which we will get back to, right? But for right now, I want to make sure that we know what we're doing with the work energy theorem stuff, okay, which is kind of, the quiz we had today was like the really easy work energy theorem stuff, okay, and not any of the more complex stuff that we've actually already done. So what we're looking for here, okay, in this one, we've got a 4,000 joules worth of work is done in carrying this box, whose mass we know, okay, carrying it up a ladder from a height of 7 meters, looking for the final height. So very similar to the first question we did on the quiz, okay, very similar to that one. So I want you guys to give this one a try, see if we get the final height of the box. All right, so we have 4,000 joules worth of work being done. Okay, so we know W is 4,000 joules. Okay, and what kind of energy is being changed here? Potential. All right, so we can just fill in that this is EP. Okay, we're going from a height of 7 meters, right, to a final height that is unknown, and we're carrying 25 kilograms worth of mass. All right, so we know that work equals M times G times HF minus M times G times HI. And this time, MGHI is not 0 because the initial height is 7, not 0. All right, so if I want to get HF by itself, which is what I'm looking for, what do I need to do with MGHI?
You need to divide it.
Nope, not divide it. What am I doing with MGHI right now? I need to add it to the other side, right? Okay, I need to add this to the other side. So I'm going to have work plus M times G times HI. So here's what we have to understand, guys. We're saying here that work is the change in energy, right? So if I take my initial energy, which is what this part here represents, and add the change, won't that give me the final amount of energy? Okay, so that's what we're saying when we do this. All right, so that's going to be M times G times HF. Now I want HF by itself, so what do I do with M times G? Now I divide, right? Okay, so I've got work plus MGHI divided by MG will give me HF. So that means 4,000 plus 25 times 9.81 times 7, so mass, gravity, and height, divided by 25 times 9.81. Okay, yes, these numbers here are the same, but they don't cancel. All right, so just be careful on that you don't accidentally cancel. Okay, so 4,000 plus 25 times 9.81 times 7, okay, divided by 25 times 9.81. Okay, so the final height of this thing is going to be 23.3 meters. Right? That is about as tricky as they might get, other than actually having to do force times distance on the other side instead of being given work like you were here. Okay. Right. Does that one make sense now? All right. Okay. This one is about as tricky as a work energy theorem question involving kinetic energy could get. All right, so give this one a try. Okay, write it down because it's a good example. I actually put one like this on the unit exam last year. All right, give this one a try. Okay, so we've got this toy car that uses a spring to propel it along a level floor. The spring is compressed 0.23 meters. What have they given me there? A distance, exactly. Okay, so we know that the distance in this question is 0.23 meters, right? And the cart increases in speed from 1.2, so we got VI being 1.2 meters per second, to 3.1, that would be our VF. Right? If the cart has a mass of 650 grams, what does mass have to be in? Kilograms. Okay, what was the force that was needed? So we're looking for F. Okay, it'll end up being 11.5. You got 11.5, you did it right. Okay, so work equals, right, our change in, and in this case, it will be kinetic energy because the car is increasing in speed, not in height. Right? So work can be calculated using force times distance, which is what we'll have to do as we were given distance and are asked for force. Okay? In terms of the change in kinetic energy, that's going to mean final kinetic energy, 1/2 mvf squared, minus initial kinetic energy, 1/2 mvi squared. All right, I want to get force by itself. What do I do with distance? Divide it over to the other side. Okay, and then we just plug in our numbers. So force will equal 1/2 times 0.65 times 3.1 squared minus 1/2 times 0.65 times 1.2 squared divided by 0.23. And when we do that, we should get 11.5 newtons for our answer. Okay. Are these all starting to look like they follow a similar pattern? Okay. They really should, because they all follow basically the same pattern. Okay. Decide what type of energy is changing. Okay. Put that in final minus initial, and then solve for what it is you're looking for. Once you figure that part out, the rest is just algebra. You just have to move things around in the equation. Right? The toughest part or the most scientific part of this is just deciding what kind of energy is being changed in the question. Okay, any questions on that one? Can I change it, or do people still need it? Okay, so 5, 7, 9, 10, and 11. I know you can't see 11 yet, but I'll move it up in just a sec when most people are done number 5. Okay, so on Tuesday, okay, you guys talked about the law of conservation of mechanical energy, right? And essentially what the law of conservation of mechanical energy says is that mechanical energy can't be created and it can't be destroyed. Once energy is put into something by doing work, that energy will always be there. It might change forms. It might become kinetic. It might become potential, right? But it's always going to be there. And the prime example of the law of conservation of energy would be like a roller coaster or a kid going down a hill on a sled. That's a really steep hill, but you get the idea. Okay, so we've got, let's say, this kid on a sled going down this hill, and let's say that the sled has a mass, including the kid, which I'm not going to try to draw. That's a toboggan, by the way, not a candy cane. Right? So the mass is going to be, let's say, 60 kilograms, and we're going to be at the top of this hill, which has a height of 40 meters. Okay, here at the top of the hill, let's say the sled is moving at 4 meters per second. Right? I want to calculate how fast the sled will be going down here at the bottom of the hill. Right? So I want to know, what is V at the bottom of the hill? What's the height at the bottom of the hill? 0. Okay. So if we're saying then that our mechanical energy never changes, okay, what we're saying is that the amount of potential and kinetic energy something has at one point, like here, is equal to the amount it has down here. Everybody okay with that? All right. Now on Tuesday, you learned that mechanical energy is actually the sum of both kinds of energy. So how much potential plus how much kinetic. All right. So how much potential you have at the beginning plus how much kinetic you have at the beginning is equal to how much potential and how much kinetic you have at the end. All right. Is the amount of potential and kinetic going to be the same? Like, if I'm looking at this question right here, at the top, most of my mechanical energy would be in what form? But yeah, it'd be potential, right? Because it's very high above the bottom, but it's not moving very fast. So it doesn't have a whole lot of kinetic energy, but it's got a whole lot of potential because it's at the top of the hill. Whereas here at the bottom, how much potential energy does it have here? Right, none. It has no potential energy because it can't fall any further. It's at the bottom now, right? All of its energy will now be kinetic, right? That's why you go fastest at the bottom, right? It's not by accident, okay? It's not by accident that you go faster as you go down a hill. You're turning your potential energy into kinetic energy. Okay, so in looking at this, the way it's set up, we just said that there's no potential energy at the bottom of the hill. So I can get rid of that. It's 0, right? But the rest of them all have a value. Everybody all right with that? Okay. So do I have a formula that calculates potential energy? What is it? Mass times gravity times height, right? Okay, so mghi, and I also have one that calculates kinetic, right? So this here would tell me how much energy I have up here in total. Whatever this is, it's the same as this, right? These two numbers, or these two sides of the equation, are equal. I have just as much energy in total at the bottom of the hill as I have at the top of the hill. Okay, so I want to calculate how fast I'm going at the bottom of the hill. So I want to find out what VF is. How can I get VF by itself? Okay, take the mass and the 1/2 and move them to the other side. How would I move them to the other side? Divide them, right? Okay, have we done a couple of questions kind of like this already with work energy theorem? Okay, similar to that. All right, so now this is gone. That solves for VF squared. I just want VF, so what do I have to do to this whole thing? Square root it. All right, so basically what we're saying is the final speed here is going to be the square root of 60 kilograms times 9.81 times 40, so that's my initial potential energy, plus 1/2 times 60 times 4 squared, my initial kinetic energy, divided by 1/2 times 60. Right? If I do that, that should tell me how fast this sled is moving at the bottom of the hill. Okay, so we've got 60 times 9.81 times 40, okay, plus 0.5 times 60 times 16, that's 4 squared. All right, and then I'm going to divide that by half of 60, which is 30, and then I'm going to square root that. Okay, don't send your kid down this hill. But yeah, that's like 115 kilometers an hour. Oh, sorry, 101 kilometers an hour. Yeah, that's not good. Okay, especially if there's like a sudden stop at the bottom, right? Yeah, it's like Christmas Vacation with the new cooking spray that he puts on the bottom of the saucer sled. If you have not seen that movie, get out from under the rock you're living under and watch that movie, because it's my wife's favorite movie of all time. She watches it any time of the year. Okay, does that sort of make sense how that works? All right, so all we're saying is that the amount of energy you have never changes. All right, unless of course you do work on something, then you would transfer it away. But you can't create it, you can't destroy it. You can give it away by doing work, you can get more by having work done on you. But if there's no work being done, energy remains the same in terms of its number. All right, now what if at the top of this hill I have all this information as well as somebody gives them a big push? Okay, so I have this energy here, this kinetic. I have this potential plus whatever work was done by the pushing. I would have to add that in because there would be more energy, right? Or if there was like somebody halfway down that grabs the sled and slows them down a little bit, well then they would lose some energy there, okay? Because that they would do work on that person. They would hit them and make them fall or whatever, right? Yeah, I wouldn't get in front of that sled. It's moving 100 kilometers an hour. It doesn't matter whether it's a little kid or not. Okay? Yeah, you're looking at a world of hurt if you get hit by that sled. Okay? Everyone kind of follow how this all works? Okay, because this is what we'll be working on probably a little bit tomorrow, but mostly next week. Right? Okay. That said, let's have you guys try one like this and see how you do on it. This is a roller coaster. I have to explain my drawings because I don't draw well. Okay, so let's say that this roller coaster is 30 meters tall and starts out moving at 7 meters per second and has a mass of 200 kilograms. And I want to know how fast it's going over here when it is 8 meters above the bottom. I want to know how fast it's going. Right? So it's a similar calculation to what we just did, except this time at the end, there is still some potential energy. Right? So remember, it's going to start off like this. The energy here is equal to the energy here. Give you a couple minutes on that one. Okay, so we have to remember that when we have mechanical energy, that we're saying that's the sum of the potential and the kinetic energy, okay, that the object has. So on both sides, it's EP plus EK. Just one side is the initial and one side is the final. Everybody okay with that? Once we write that, then we got to decide, does it actually have all of those types of energy, or are any of them zero, and can we simplify our life a little bit? Unfortunately, in this one, we can't simplify our life, okay? Because at the beginning, it's moving at 7 meters per second, which means it does have kinetic energy, right? It's also 30 meters above the ground, so it also has potential energy, right? At the end, it's still 8 meters above the ground, so it has potential, and we're trying to solve for VF. At this point, it would likely be moving faster than it was at the beginning, meaning it also has kinetic energy. Everybody all right with that? Okay, Evan.
You just get the kinetic energy by minus the energy from the initial since they're balanced.
We're going to do that. That's the first step, actually. Okay, but kinetic energy isn't what I'm looking for. I'm looking for the speed, which is part of that. Yeah? All right, so as Evan was saying here, could I just subtract this potential energy here over to the other side? Yes, I can. And that's actually the first thing I want to do. That'll get the kinetic energy, which has what I'm looking for in it. So I'm going to move the potential energy over here by subtracting it over. So I'm going to have EP initial plus EK initial minus EP final equals EK final. So all I've done is subtract the potential energy over here. All right, so I'm saying the mechanical energy minus the potential energy equals the kinetic energy. All right? Do I have formulas for all of those things? Yeah, so I'm just going to put those in. That's my next step. M times G times H initial plus 1/2 MV initial squared minus MGH final. That's going to equal 1/2 MV final squared. All right, so that's what I'm looking for there. Okay, so I'm still looking for VF. Okay, I'm looking for the final speed. So how do I get VF by itself now? Okay, divide. Exactly, divide 1/2 M over to the other side. Okay, so now that's gone, and I'm solving for VF squared. I just want VF, so I'm going to square root. All right, so this gets a little bit hairy in terms of how much stuff is in there, but okay, in the end, they're almost always this, like, kind of the same idea, just like work energy theorem questions were. All right, so VF is going to be then, what did we say the mass of this thing was? 200? Okay, so 200 times 9.81 times the height, which was 30, plus 1/2 times 200, the mass, times the initial speed, 7 squared, minus my final potential. So 200 kilograms times 9.81 times the final height, which was 8. And then divide all that by 1/2 times 200. Right? Now, if you're like a math whiz, you've probably noticed that every single term is multiplied by 200. Could I take 200 right out of there if every term is multiplied by it? Yeah, just take, yeah. Well, actually, you can just cancel it, right? M is in every single one of these terms. You could actually cancel M all the way off and not even have to have it in there, right? If you're comfortable with that, you can do it. If you're not comfortable with it, leave it in there. It doesn't change the answer. You'll actually get the same answer no matter what. Right? Okay, So now I've got all of that stuff entered in there. Okay, I just need to calculate what it comes out to. So we'll have 200 times 9.81 times 30 plus 1/2 times 200 times 7 squared minus 200 times 9.81 times 8. All right, divide that by 100. That's half of 200, and then square root that. All right, that's a reasonably fast roller coaster. Okay. At the end there, when it's still 8 meters above ground level, it's going to be moving at 21.9 meters per second. Yes, the sled's faster because there was a taller hill, right? And of course, this is all assuming there's no friction or anything like that to slow you down, which in the real world, of course, there always is.
And higher levels, will you have to account for friction?
With that?
And higher levels, will you have to account
Yeah, altitude doesn't affect friction. What affects friction is the nature of the two surfaces and the mass.
So like in grade 12, will you have to account
No. Alrighty, I think we'll leave it at that for today. Okay, tomorrow we're going to work on a few other kind of different things. Okay,